So there's a lot of hype going on with AI and machine learning. It's permeating, all fields, all research, science, commercial. It's everywhere. So why not communications too? So in fact, right now DARPA is doing a grand challenge called the Spectrum Collaboration Challenge. The idea is, how can we use AI to access the spectrum? I have a team. One of the finalists. Next month we're heading to the Mobile World Congress to crown the champion in this competition. And when I started this, I had this fantasy, right? This fantasy of, we're going to make this chip smart, right? We're going to take software radios. We're going to go down into just as deep as we can go, and we can make it as smart as possible. But instead, what happened is all the teams got together, and we had a lot of arguments about compliance, right? In order to participate in this competition, you had to be compliant, right? So radios that weren't good enough, they would just remove from the competition. So there's a lot of talks about compliance, which ended up being okay because I've always, in my mind, this is kind of my vision of radios of the future. Whereas right now you have these stickers that go on wireless devices. Have you ever seen this, where it says you can't transmit so much power and you have to be able to accept power, right? So this little sticker on the left, right? We see that all the time on wireless devices. But that's really dumb, right? Essentially what they're saying is intelligence is just don't transmit very, very strong, right? So what I envision is in the future, our wireless devices are going to have the sticker on the right, which says that you need to demonstrate a certain amount of intelligence in order to access the RF spectrum, and you need to be able to respond to intelligence, right? That makes a lot more sense. But what is radio intelligence? That's what we're going to talk about. So I broke this down, just to make it easier to talk about, I broke this down in 3 areas regarding radio intelligence. The first is where and when to transmit. That's kind of your cognitive radio idea. If there's an opening in the spectrum, go ahead and transmit there. Raise and lower your power, adapt, when to transmit, things like that. So that one is kind of what the DARPA challenge is all about. Is kind of this higher layer of intelligence, which is not what I'm going to talk about today. On the right, I broke out bits. I wanted bits to be its own thing, right? So as soon as you get to bits, whether it's error correction or encryption or what the bits mean, to me that's something else. And what we're going to talk about today is what's in the middle, which is how to transmit the bits across the channel. All right, so that's waveforms, spreading, hopping, things like that. Okay, so when I talk about radio intelligence today, even though I understand that it spans all parts of this, today we're going to essentially talk about the physical layer of intelligence. So this is my dream. There was a guy named James Maxwell. He's very famous. He has a cool set of equations that are important to what we do. He also had this philosophical concept called Maxwell's Demon. Maxwell's Demon is the idea is if you have a little demon in a box, and he can control this gate, and as soon as a fast molecule or a hot molecule gets close to the gate, he'll let it through. If a cold molecule comes through, he'll shut the trap. So keep all the cold molecules on one side, all the hot molecules on the other side, and then entropy is violated, right? So physicists don't like that. So that's called Maxwell's Demon. So my idea was Com's Demon, right? So let's say we had a daemon now inside of a universal hardware. And what this daemon does is you put this hardware into some environment and you give it some objective. And let's say that objective is minimize your bit errors, right? So you give the daemon a bit, and the daemon goes through and decides exactly what the sample needs to be for that bit and for all previous bits. And then you transmit that sample across the wireless channel, right? So you get rid of, you abstract out all of essentially communications, all the filtering and so on. You abstract it out, and this daemon just takes bits and he spits out samples. Right? So that's Com's Demon. That's what we're trying to make. So I tried to make it, right? I tried to make this little daemon guy. So what I did was I got my software radio, I got GNU radio, and I broke out these 3 parts of intelligence. Up there at the top, that's where the bits come in. It's just a socket that you can connect to any sort of application that you want to. that also has the same socket. Those bits come in. That bottom layer there is kind of, the where-when. You know, you set the frequency, you set the bandwidth, you set the sample rate, you set the power. That's kind of the hardware. But where all the action happens is right there in the middle. That's where the daemon lives, right? So that daemon is going to take bits from the application, and it's going to turn that directly into samples, which is going to transmit across the channel. Okay, so that's the goal. So I did this. These results are actually from 2018, so they're a little bit old. I presented them last time, but just to go over it again, just so you remember where we're at. So the first thing I did was I made the daemon. We call it Deepmod, for deep modulation. And we coded it up, and we put it in some hardware. And for fun, we used a speaker microphone system. So rather than using RF energy or antennas, we used sound, just because we actually wanted to listen to it, learn how to talk. We wanted to hear what it came up with. So instead of bits, we use phonemes, so like of the English language. And so we have these two nodes here, these two Deepmod nodes with their software radios. We turn them on, and they start talking to each other over the air. And after some amount of time, they arrive at a shared language that they then use to communicate information. Okay? So that was fun to listen to. We took that same daemon, Deepmod, and we put it over the power line. So the idea is you throw out the speakers and the microphones, and we just plug our little B210 there directly into the wall. So if you have a power outlet over here, you plug in over here, another power outlet over here, you're on the power line channel. We turn them on, they start sending energy back and forth to each other. They don't know what that energy is at first, but after a few training epochs, they've decided this is what you're trying to tell me, and they've come up with a physical layer protocol that can communicate with each other. And then finally, the classic RF channel. Now we put antennas onto the radios. We crank up the frequency to 900 megahertz, and we start transmitting. Okay, so remember that there is no signal processing going on, right? That one GNU radio block, which is a neural network, takes care of all the processing. Right? It learns everything it needs to about the channel in order to communicate bits wirelessly. It's pretty cool. It's fun to watch. So as I show this to people, nobody believes it works, which is fine. In fact, I come from academia, and I ran a simulation with Deepmod, and I'm like, whoa, this is cool. I mean, this machine is learning, it's essentially replacing all this human code. It's just learning it itself. And so I'm like, I got to stop doing simulations. It was too fantastic, right? It's too unbelievable. So after one simulation, I just went straight to over the air from then on out, right? I had to actually build it and do it, or nobody would believe me. So some questions I don't like. So don't ask me this. What does the Deepmod constellate? I hate this question. There is no constellation, right? There's no idea of constellations, right? The machine just decides directly how to map the bits to the samples. There's no intermediate idea of constellation. What equalizer does it? There's no equalizer, right? It just takes care of that in one of its network layers. I don't know where, but it's in there somewhere. How does it handle carrier frequency offset? Aha, right? They think they've got me. What about CFO? I don't know. It just does. A lot of these machine learning people want to know, why can the machine tell you that that's an apple and that's an orange, right? Why do they do that? That's called meta learning. I don't care. I don't care. Because it works, so I don't care. Another question I don't like is, well, how does it compare against, a human system, right? So humans have spent a long time on digital comms, and you're saying we're just going to throw out all the humans, replace them with machines. So how does it compare? So the reason I don't like this is I can't win. I can't win this, right? If I say that in simulation Deepmod does a little bit worse than, say, BPSK and AWGN, they're like, it does worse. I'm like, yeah, okay. I mean, because BBSK is optimal in this very simplistic channel. Now, if I do it over the air, and then Deepmod does better, then people are incensed. And they said, well, if you were just to change your equalizer, or if you were to tweak beta, or you to do this and this, and all that, we've all played this game, right? You tweak all these parameters, then maybe the human machine would do better. Which is true, but that's the whole point. Mine didn't have to do that, right? It learned on its own how to communicate, which is the whole point. So what we should ask is Deepmod intelligent? Right? Is this radio, is it an intelligent radio? So we have a couple things that we can go off of in the past. Something's called the Turing Test, right? I think we've all heard this before. And it's a test of a machine's ability to exhibit intelligent behavior equivalent to or indistinguishable from that of a human. So, for example, the imitation game. So if you're Tune A here and you're playing Surviv.io, you know you guys play it, right? You know, Fortnite's down, you got to play something, so you go play Surviv. And so Tune B, so you're hiding in the house, Tune B is outside the house. And you want to figure out if Tune B is a bot or if it's a human, right? So how do you do that? Well, you ask it a series of questions, and depending on how it responds, you decide, oh, you're a human or you're not a human. So you say, hey, you want to team up? And if Tune B says, sure, come out of that house and we'll own some stuff, right? You got to decide, is that a bot or human? It's obviously a bot because it's spelled own with an O instead of a P, right? So don't you stay in that house, right? So the hard part of the Turing test is figuring out what the questions are. What's the suite of questions we're going to ask? And then based on the responses, how are we going to determine whether that's a human, right? So those are the hard parts of the Turing test. Next, we have the Captcha Test, which we've all seen. And this is, you're registering for some website. They run this test by you trying to figure out whether you're a human or not, because they don't want bots filling up their database or something. So it's kind of a counterpart to the Turing test. The Captcha test is now a computer deciding if you're intelligent, rather you deciding whether a computer's intelligent. And then there's something I call the Dr. Anderson test. So I'll teach a class on machine learning, and everybody loves it. Not because I'm teaching it, but because machine learning is just this great thing. And I encourage them as one of their projects is to apply machine learning to whatever they're doing. I don't care what you're doing. I don't care. Whatever your field of study is, apply machine learning to it. So these students will come to me and they'll say, Dr. Anderson, do you think I could code this up to automatically classify? They'll bring some data set to me or some picture or something. They'll say, can we make a machine classify this, right? And so my first question is, well, can you classify it? Because if you can classify it, chances are we can come up with a machine that can classify it as well, right? So that's my first step is, can you do it? So for example, this digit here on the left, it's a 0, right? So if a student were to come to me and say, hey, look, can we come up with a machine that can classify these digits? My question is, well, can you classify it? Like, yeah, it's obviously a 0. Well, then we can come up with a machine to classify it too. This image in the middle, this is data from URE, unintended radiated emissions. All electrical devices radiate something, whether intentional or not. And so he'd been working on it so long that he could look at this data set here in the middle, and he could say that's fluorescent lights, right? And not a monitor, and not an Xbox, right? Just because he'd been working on it so long. So when he comes to me and shows me this picture and says, can we create a machine that will just tell us that this is fluorescent lights? I asked him, do you know it's fluorescent lights? And he's like, yeah, well, sure. We can make a machine to do it, and we did. The picture on the right, that's my little girl, my second little girl. I named her Shannon after guess who? Yeah, that's right. I also have a Tesla, but not named after the car. Everybody says that. Named after the car? No, she's not named after the car. So I didn't know this before. This is maybe I'm new to PowerPoint, but if you put an image into PowerPoint, it'll suggest text. Alt text. Have you guys ever done this? So I pasted this picture into PowerPoint, and this was the text that Microsoft suggested: a girl on a swing, right? Wrong, right? She's not on a swing. What is she doing? Can you see? What is she doing? Can't tell? Not a very good image. She's not on a swing. What she's doing, there's two issues. One is what she's holding is too rigid, and it's made of wood. And if you look in the background, there's these things on the ground called leaves, right? So if you were to take that into account, that the fact that there's leaves in the background and she's holding something rigid, you'd actually say a girl holding a rake, right? That would be a better caption for that image, right? So if Microsoft came to me and said, "Oh, hey, Dr. Anderson, do you think we could ever come up with a machine that can classify this correctly?" And I'd say, "Oh, Microsoft, go try again, because you can do it. Therefore, eventually we'll be able to make a machine that will classify that correctly." So what do we have? We have the Turing Test, which is a human guessing if a computer is a human, the Captcha Test, which is a computer guessing if a human is a computer. And then we have Dr. Anderson's test, which is if a human can do it, then so can a computer, right? And just one observation, that determining whether a radio is intelligent or not might be easier than human intelligence, because we don't care how the radio does it, as long as the behavior is similar to what a human does. Does that make sense? Whereas with the Turing test, how they say it and what they say is as important as what the answer is. For radio intelligence, we don't care, right? The radio doesn't have to come up with OFDM if we give it the objective of beating frequency selective fading, right? As long as it comes up with something to defeat it, that's good enough. That's an intelligent radio. So for now, just for the purposes of this talk, we're going to say a radio system is intelligent if a human, given an unlimited amount of time, could derive a similar system, similar behavior for that in particular environment. Okay? So if I put this radio in some funky environment and I turn it on and it functions well, and if a human could come along as well, model the environment, spend a lot of time, write a lot of papers, get a lot of funding, go through this entire process, and then come up with a radio system that's similar, then we'll say, okay, well, the radio was intelligent, right? It came up with what the human might have come up with as well. So we have man versus demon. Okay, so the next two slides, I apologize. There are 4 non-technical people, so you guys are going to roll your eyes at this, and I apologize. But it's important for one point. So what I say is this little black cloudy thing represents 4 bits. Okay, and it's a cloud because it's noisy, right? So we want to put 16 of these things into this little fenced area, right? And we want to put them as far apart as possible, because if they get close together and if they ever overlap, we get bit errors, and that's bad, okay? So I asked them, I say, how would you arrange 16 of these little black cloud things into this square so that they're as far apart as possible, right? It's a little thought exercise. And really, you can ask a 6-year-old this, and they can come up with an arrangement of 16 of these. So they're as far apart as possible. And we've done it, right? It's called 16 QAM. And the reason it's shaped like that is because a human came along and decided that that's the optimal, the maximum distance. So I gave a machine this exact same problem. So I went to the machine and I said, I created some neural network, and I said, here's some noisy symbols. And I passed them through the neural network, and I said, how would you arrange it, right, if you were going to do it? Right. So this is what the machine came up with. Yep, 16 QAM. Of course it is, because that's what you would do, right? It's a little crooked. Maybe if I'd let it run for a little bit longer, it would have evened up and come up with a solid. Actually, what I would have had to do is make it noisier, right? Because if that's as much noise as there is, it thinks that's good enough, so it stops. It's like, there's no overlap. I'm done. So now let's put it in a different environment, right? So now instead of having nice, white noise, we have correlated noise. For whatever reason, I made it up. Maybe there's more noise in the real direction than in the imaginary direction, right? So now if you were to put these 16 symbols in this environment, that's bad. You do very poorly, right? Lots of overlap. It wouldn't perform very well. But you're stuck with 16 QAM because that's what the human coded it up, right? But the machine doesn't know about 16 QAM. It just knows about what environments it's in. So if we put the machine in the same environment, this is what it comes up with instead, right? So instead of 16 QAM, it comes up with some weird 8 by 2 QAM. Because that makes it happy. That makes the machine happy. It maximizes the objective function of lowering the bit error rate. Okay. So the same machine, remember this is the exact same machine. The code did not change. No part of it changed. The only thing that changed was the environment that it was in, right? So you move the daemon from here to here, comes up with an entire different physical layer, okay? So now this is important, very important. Take this, this is the takeaway. So you could say, well, we could have made a radio that had modulation adaptation, right? Maybe had 16 QAM and BPSK in it, and we would have just switched to BPSK. And that's cool. That would have been adaptive, right? If you could do that, we'll call that adaptation, right? But inventing 8 by 2 QAM in situ, on the fly, that's intelligence, right? Because it didn't exist. It didn't exist until it was made to learn that, and then it becomes intelligence, okay? So what we need to do then is again, this is just, I'm not saying this is how things should be. This is what I did. I came up with a suite of tests, questions that I'm going to ask my radio and then see how it replies to figure out if it's intelligent or not. So I came up with, I didn't do it. I'm not showing you all of them, but I came up with a few. And here's the first one. So the first one is, if we take our radios, and let's say we put it into a congested environment. So let's say there's a narrowband jammer there for whatever reason, right? So you have two radios, environment, narrowband jammer. What would a human do? Well, in this case, a human, maybe it makes a notch filter on the front end, you know, remove that interference. If it's an OFDM system, maybe it suppresses that carrier, right, so it doesn't transmit. There's lots of things a human might do to solve the problem. So I did this with Deepmod. Got my two radios, put them in the environment, turn on the jammer. So what you see over here, this plot on the right, is the performance of Deepmod versus time. So when you first turn it on, it does terribly. Takes about 200 epochs, and it trains up to 100%. It's sending bits across the channel perfectly, right? All on its own. At about epoch 400, I turn the jammer on, kills the communications, right? But it doesn't stop learning. So give it a few hundred more epochs, and all of a sudden, with the jammer there, it's communicating again, okay? Not because we ever taught it to communicate with the jammer, but because it taught itself how to communicate with the jammer. So the question was, how are you going to react to a jammer? This is its response. And we have to decide, was that an intelligent response? What about a relay channel, right? Get a little funky here, right? So I added really simple. I don't work with relay channels. I'm not an expert. I just got a third node. It's dumb. Just amplify and forward relay channel. So whatever signal it gets, it moves the frequency down a little bit and then retransmits it. Right? That's all the relay does. And there's a lot of work. If you Google this, there's a lot of work of what humans have done for the amplify and forward relay channel. So what Deepmod did was, so I set them up so they're far apart, so they can't. There's no direct communication, right? They can only communicate through the relay in the middle. They start training back and forth through the relay, and honestly, it didn't even affect it at all, right? They had no idea. They had no idea they were in a relay, because I never told them that. They just learned to communicate with the relay. So I call this the Lone Survivor channel. I've never seen the movie, but apparently these guys get caught behind enemy lines or something, and then they can't. They each have radios, but they can't reach headquarters. Is this even close? And the idea is, well, maybe if they were able to cooperate, then they would have been able to reach home base or something. So what would a human do in this case? Well, there is something called the cooperative MIMO channel, right? And maybe these radios could share CSI with each other. If you had some really good synchronization, you could learn to transmit so the signals constructively add over the air, and then you could get some gain out of it, right? Cooperative MIMO. So what did Deepmod do? So in this case, what I did was I got a third node again. Now I made it smart. So I took that dumb relay, wiped it, installed Deepmod on it. And this was amazing. I mean, this was amazing. The only change I made was 2 of the nodes, I called them Deepmod 0, right? So they both think they're Deepmod 0. And the other node I called Deepmod 1. And then I turn them all on at the same time. So they start talking back and forth, start training each other on how to communicate over the air. And at first, it's just nonsense, right? Because they all start out, they don't understand how to send information. But then eventually, the 2 Deepmod 0s, they eventually started lining up their transmissions on their own, so that they got the extra gain out of cooperation. And it was really fun to watch. It's fun to watch that, and I just did this in the morning, right? Just one morning, I thought, oh, I wonder if it would work this way, right? So again, is that intelligent? Mobility, same idea. What happens if you take your supposedly intelligent radio and now you start moving around? What happens? So mobility causes fading and environment changes. Humans have been looking at this for a while. There's a lot of solutions on how to handle mobility. For Deepmod, I put one of the nodes in a hotel room. I put the other Deepmod in the back of a car, and we just started driving around town with it. And it's cool. And what we found is that it's very similar to the jammer, is that if you drive around a corner or something, if you change the environment a lot, it would stop communicating until it trained for a little bit, and then it would get back up to normal. So, and eventually, I'm sure there's a velocity where you couldn't train fast enough to keep communications going. This one was fun. I thought, well, what if we want to require that Deepmod is also narrowband for whatever reason, right? So I googled narrowband spectral envelope, and I got some picture over there on the left. And I thought, well, what would a human do to have an envelope like this? Well, usually the envelope just comes from whatever modulation you're using, just kind of a natural consequence. So it's kind of a silly question. But if you wanted to, you could take your packets, you could pulse, you could packet shape to get a shape like that. You could add artificial noise to get the little side lobes if you want. I mean, there's things you could do so that whatever you're transmitting looks like that image on the left, right? So what did Deepmod do? Well, so I told Deepmod, go ahead and keep minimizing the bit error rate. That's what I want you to do. But I picked certain points in the spectrum, and I said, while you're minimizing the bit error rate, I also want you to look like this. Okay. So I turned it on, and he starts out pretty flat, but it's fun to watch him as he's training with the other node. The spectrum kind of start dropping down and looking like what you want it to. And I really like that. See the little dimple in the middle, little dimple at DC. I thought that was kind of cute that it decided to put that little dimple there. And then the last test, not the last test I'll share with you guys, is spectral efficiency. So again, let's put some radios in an environment, teach them how to talk, or have them learn how to talk, and then tell them that they're allowed to have more samples per symbol or lower spectral efficiency. See what they do, right? Now humans have been working on this forever. Different types of codes. You could spread the bits a little bit, get a little bit extra performance that way. So there's a lot of things you could do if you give the radios some extra spectral efficiency to work with. So with Deepmod, I did the same thing. I got some baseline. I call it uncoded. And then I had it retrain at different. It's hard because it's not really a code rate. For the 1/2 and 1/3, I told Deepmod you could have twice as many samples per class or 3 times as many samples per class. Okay. And so then what it did was it learned that with that extra freedom, you can lower your bit error rate more. Right. Which is pretty cool. Which is neat that it learned how to do that on its own without being told. And so I was thinking, you know, if Shannon and Turing were still alive, right? I could see Shannon making fun of Turing, saying, "Oh, you know what? We already have machines that pass your test, like it's no big deal." But then Turing can tell Shannon, "Well, a machine just told us that for fixed SNR and code rate, you can get an arbitrary low bit error rate." Right? And they can duke it out about how machines are taking over. Not just physical labor and stuff, but machines are taking over intellectual discoveries. So, conclusion. In the future, I suspect that there will be bands of spectrum that will require some form of intelligence in order to be allowed to access it. So we need to have a test. We need to develop a test that says whether or not a radio is intelligent. And I think that's our responsibility. That's something that we should take the lead on, is defining what is an intelligent radio. So the idea is we need to give these radios this test, ask them these questions, put them in these environments, see how they respond to it, and then we decide, yes, that's sufficient intelligence to call the radio an intelligent radio. That's it.
All right, thank you very much, Adam.
Yeah.
Hi, thanks for the talk. It was interesting. What if you were to set the objective to be undetectable, or like try to make it come up with stenographic protocols, like noise?
Yeah, the idea of multiple objective functions, machines, take that in stride. It's no big deal. In fact, I've given Deepmod 6 different objectives, and it achieved all of them. So the idea of be below the noise floor, be undetectable is something we've looked at. Yeah.
Yeah. Hopefully it works for you.
Thank you. Did you find that the system learned to lean on one mechanism more so than others as it was learning the whole process of what it could change to achieve its goal?
All right. Thank you very much, Adam.